Hello math friends, this is section 4.5 day 2 notes for AP Calculus. Today we are still talking about indeterminate forms, and specifically today we are going to start with indeterminate differences. So let's say we have a limit such as the limit as x approaches infinity of f of x minus g of x. And when we do direct substitution we get something like infinity minus infinity. So this is again like a contest between f of x and g of x, and we don't know which result will win. But if we can convert the limit into the form of a quotient, then we can use Hopital's rule to evaluate the limit. So when we think about trying to turn something into a quotient, we're often thinking about either factoring, rationalizing, or finding a common denominator. Okay, so those are kind of the tricks in our bag that we have for converting our limit into the form of a quotient. So let's take a look at example 1. So when I begin, the first thing I do is check. If I were to plug in 0, cosecant of 0. Now cosecant, remember, is 1 over sine. So 1 over sine of 0. Sine of 0 is 0. 1 divided by 0, though, that's infinity. So cosecant of 0 goes to infinity. And then cotangent is cosine over sine. And when I plug in 0, cosine of 0 is 1. Sine of 0 is 0. 1 divided by 0, again, that goes to infinity. So I end up with this indeterminate form, infinity minus infinity. Okay? So this is just an indicator for me that I'd like to try Hopital's rule, but in order to do so, I have to make this limit look like a quotient first. So let's start, since we have trigonometric functions here for f of x and g of x, let's start by turning everything into sines and cosines and see where that gets us. So this would be equivalent to the limit as x approaches 0 of, we already said cosecant is 1 over sine x, and cotangent is cosine x over sine x. So it looks like I have two fractions that already have a common denominator. So I could rewrite this as the limit as x approaches 0 of 1 minus cosine x divided by sine x. Okay, so now that I have a quotient, let's check and see if I have an indeterminate form. So in my numerator, if I plug in 0, cosine of 0 is 1, and then 1 minus 1 is 0. So my numerator does go to 0. And in my denominator, sine of 0 is 0, so my denominator goes to 0. So I do indeed have a 0 over 0 indeterminate form. So now, using Hopital's rule, I can rewrite this limit as the derivative, the limit of the derivative of the numerator's function divided by the derivative of the denominator function. The derivative of 1 minus cosine x, well, the derivative of 1 is 0. The derivative of cosine is negative sine. So I'm going to have negative sine x in my numerator, which is just positive sine x, but I'll simplify that in a second. And then the derivative of sine x is cosine x. So I have the limit as x approaches 0 of sine x over cosine x. So now let's check again. What do I have? Well, sine of 0 is 0. But cosine of 0 is 1. So if I have 0 divided by 1, I no longer have an indeterminate form. So I'm going to go ahead and do my direct substitution. This is going to be sine of 0 over cosine of 0. And sine of 0 is 0, but cosine of 0 is 1. And 0 divided by 1 is 0. So the answer to the limit in example 1 is 0. In example 2, we have what looks like some sort of a square root situation here inside of our limit. But again, let's first check what we get when we plug in infinity. So under the radical, infinity squared would be infinity, plus infinity would be infinity, and the square root of infinity would still be infinity. So this part is infinity minus, and if I'm plugging in infinity, it's infinity. So it's infinity minus infinity. This is one of those situations where we'd like to use Hopital's rule, but first we have to rewrite this in the form of a quotient. Okay, so since we have a square root, my thought is let's try rationalizing. So the first thing I'm going to do is I'm going to multiply by the square root of x squared plus x in the top and in the bottom. Okay, and now when I do that, I have the limit as x approaches infinity. In my numerator, when I FOIL that, remember I just have to do firsts times last. Square root of x squared plus x times square root of x squared plus x just gives me x squared plus x. And then negative x times positive x gives me negative x squared. And then in my denominator, I have that family of the square root of x squared plus x plus x. But at least in my numerator, I've created something that looks a lot nicer because my x squared and my negative x squared cancel. So now I just have x, right? So now let's rewrite this over here. I have my limit as x approaches infinity of x over the square root of x squared plus x plus x. Okay, and now let's do another check. If I were to plug in infinity, in my numerator, it would go to infinity, and in my denominator, it would go to infinity. So now I have infinity over infinity, which is a situation where I could use L'Hopital's rule. So let's try it and see what we get, okay? So if I'm going to apply L'Hopital's rule, the derivative of the numerator is just going to be 1. So I'm going to have the limit, don't forget your limit notation, as x approaches infinity of 1 over. Okay, now the derivative of the bottom. This is a little more complicated. So that square root of x squared plus x, that is x squared plus x. Here, I'm going to write it underneath it. This is x squared plus x to the 1/2 power, right? So the derivative of that would be 1/2 times the square root of x plus x to the negative 1/2 power times, chain rule, the derivative of x squared plus x. Okay, so that's going to be 1/2 times x squared plus x to the negative 1/2 times the derivative of x squared plus x, which is 2x plus 1. That's just the square root part. And then plus x, well, the derivative of x would be 1, so that's plus 1. And this is all in my denominator. All right? So now what happens if I plug in infinity? Well, I have a bit of a problem here because in the denominator, if I rewrite this before I try plugging anything in, I've got the limit as x approaches infinity of 1 over. And then let's see, that first term in my denominator, I've got 2x plus 1 in the top. And in the bottom, I have the 2 from the 1/2. And then the x squared plus x is to the negative 1/2 power. So underneath the fraction bar, it's going to be the square root of x squared plus x. That's the first term plus 1. And all of that is in my denominator. So now when I check by plugging in infinity, the problem is I still get this infinity over infinity right here. Okay? And so, this is very messy right now already. And we still have 0 over 0 in our denominator. Whoops, I'm sorry, we still have infinity over infinity in our denominator. Okay, so the thing is we could do L'Hopital's rule again, but we would first have to simplify this, and it would take a lot of really messy algebra. So at this point, let's backtrack for a second, okay? Let's go back to the point in the problem right here, the blue part of the problem, okay? Let's go back to that step right there, and let's go back to our limit roots here, stuff that we learned earlier in the year. If we wanted to evaluate a limit like that, when we're evaluating at infinity, our trick was often to try to divide by the greatest power of the variable in the denominator instead. So if I did that instead, what if I write the limit as x approaches infinity of, okay, and now the greatest power of the variable in the denominator is x, right? Under the radical, it's x squared, but outside of the radical, it's x. So in my numerator, I would have x over x, and in my denominator, I would have the square root of x squared over x squared plus x over x squared plus x over x. And when I simplify that, where does that get me? Let's see, the limit as x approaches infinity of 1 over the square root of 1 plus 1 over x plus 1. And so now when I plug in infinity and I do direct substitution, we know that whenever we divide by infinity, it always goes to 0, right? So this term right here goes to 0. And so I end up with, when I plug in infinity, 1 over the square root of 1 plus 0 plus 1. 1 plus 0 is 1, square root of 1 is 1, 1 plus 1 is 2. So I end up with the answer to my limit being 1/2. So this is a great example of a situation where we started out thinking that we were going to do L'Hopital's rule. But after trying it, we found that maybe that wasn't the best route, and maybe this was a problem that was best done algebraically or done the old-fashioned way. And so then we went back to our limit roots of let's divide by the highest power of the variable in the denominator. All right, now we're going to change gears a little bit, and we're going to talk about indeterminate powers. So what if we're trying to evaluate a limit where x is approaching some value of a function raised to a function, and we get some sort of indeterminate form like 0 to the 0 power or infinity to the 0 power or 1 to the infinity power. Okay, those are all still what we would consider to be indeterminate forms as far as limits are concerned. There is an important note here. Note that 0 to the infinity power is not indeterminate because this would still have a value of 0. 0 to any power is 0, right? But for any of the other three types of indeterminate situations, we can use something new. We can use natural logarithms to convert the limit to a form where we can then apply L'Hopital's rule to evaluate. And again, remember, to apply L'Hopital's rule, we need to have a quotient. And our quotient needs to be 0 over 0 or some form of infinity over infinity. All right, so let's take a look at our first example, and we're going to go through this process slowly and carefully because it's going to be the first time that you've seen this trick where we're going to use natural logarithms to evaluate this limit. Okay, so our original given limit is the limit as x approaches 0 from the right of a function to a function of 4x plus 1 raised to the cotangent x power. Whenever you have a function raised to a function, you're going to need to use the following process, which is using natural logarithms to try to solve the limit. Okay, so our first step is we're going to name this limit y. So we're going to say let y equal the limit as x approaches 0 from the right of 4x plus 1 to the cotangent x. So basically we're saying we're just going to give this limit a name and we're going to call it y, and so now our job is to solve for y, right? Finding the answer to the limit means finding y. And the next step is we're going to take the natural log of both sides of the equal sign. So I'm going to write the natural log of y is equal to the natural log of all of that stuff. The limit as x approaches 0 from the right of 4x plus 1 to the cotangent x power. And then we're going to think about our limit laws, and we're going to think about our rules about limits. And we can pull the limit out in the front of the natural log, okay? So that's going to be our first step here, is this limit is just going to get moved in front of the natural log. So then we're going to have natural log of y is equal to the limit as x approaches 0 from the right of the natural log of 4x plus 1 to the cotangent x power. And then our next step is going to be to use the laws of logs to bring that exponent down in the front, right? So then we can take this cotangent x exponent and we can move that down in front of the natural log. So then that's going to give us natural log of y is equal to the limit as x approaches 0 from the right of cotangent x times natural log of 4x plus 1. We're getting closer, okay? We still are trying to make a quotient here, though. So the way that I would make a quotient is I would say, well, a cotangent is the same as 1 over tangent. So I could rewrite multiplying by cotangent as dividing by tangent. Okay, so that takes us to our next step here, which is natural log of y is equal to the limit as x approaches 0 from the right of, so I'm going to have natural log of 4x plus 1 in the top, and then I'm going to have tangent of x on the bottom. All right, now that I get to this point, I finally have a quotient, right? So let's check our quotient and see if we have an indeterminate form. So when I plug 0 in, 4 times 0 is 0, and 0 plus 1 is 1, and the natural log of 1 is 0. And tangent 0 is sine of 0 over cosine of 0, which is 0. So I do have my indeterminate form of 0 over 0. So now, Hopital's rule, okay? So when I do Hopital's rule, then I'm going to have natural log of y is equal to the limit as x approaches 0 from the right of, and now I have to do the derivative. Well, the derivative of the natural log of 4x plus 1, okay, remember derivatives of natural logs, maybe it's been a while, is 1 over the stuff times the derivative of the stuff. So in my numerator, I'm going to have 1 over 4x plus 1 times, and then the derivative of 4x plus 1 is 4. And in my denominator, the derivative of tangent x would be secant squared x. And since I'm dividing by secant squared, dividing by secant squared is the same thing as multiplying by cosine squared. So I could simplify this complex fraction a bit by just saying that dividing by secant squared is the same as multiplying by cosine squared. So I still have natural log y is equal to the limit as x approaches 0 from the right of, I have the 4 times cosine squared x over 4x plus 1, right? So I just rewrote secant squared in the denominator as cosine squared in the numerator. And now I believe I can do direct substitution, because if I plug in 0, cosine of 0 is 1, 4 times 1 gives me 4 in my numerator, and 4 times 0 is 0 plus 1 is 1, which gives me 1 in my denominator. So I no longer have an indeterminate form, okay? So when I do that, I am going to have on the left still natural log of y is equal to, and again, when I do direct substitution, I'm going to have 4 times cosine squared of 0 divided by 4 times 0 plus 1, which is going to give me natural log of y is equal to, again, cosine of 0 is 1, 1 squared is 1, so this gives me 4 times 1 over 1, or natural log y is equal to 4. Okay, now we're not done. We're almost there, but we're not done, because remember, we took the natural log of y so that we could do all of this fun stuff to try to create a quotient so we could use Hopital's rule, but now we have to undo that because we're trying to solve for y. Y was our limit, right? And we're trying to solve the limit. So now the next step is going to be, if we want to undo the natural log, then we have to raise both sides with a base of e, right? So the next step here is going to be e to the natural log y is equal to e to the fourth. And the e and the ln cancel out. And so then we get y is equal to e to the fourth power, which is the answer to our limit. So therefore, y is equal to the limit as x approaches 0 from the right of 4x plus 1 to the cotangent x power, which is equal to e to the fourth. Wow, those problems are a lot of work, aren't they? All right, let's try one more example to make sure we've got this natural logarithm, L'Hopital's rule stuff down. So in example 4, we are taking the limit as x approaches 0 of 1 minus 2x raised to the 1 over x power. Again, we have a function raised to a function. If we were to plug in 0, we would get 2 times 0 is 0, so 1 minus 0 is 1, but then 1 divided by 0 is infinity, and we have 1 to the infinity power, which is an indeterminate form. 1 to the infinity power does not mean infinity, okay? It just means let's do some more work. So we're going to start by letting y equal our limit. And then we're going to take the natural log of both sides of the equal sign. So ln of y is going to be equal to ln of the limit as x approaches infinity of 1 minus 2x to the 1 over x power. And then just like we did in the last problem, we are going to move the limit to the outside, right? So basically swapping the positions of the natural log and the limit, because the limit of the natural log is the same as the natural log of the limit. So ln y is going to be equal to the limit as x approaches 0 of the natural log of 1 minus 2x to the 1 over x power. And now we're going to use the properties of logarithms to bring that 1 over x power in front of the log. So we have natural log y is equal to the limit as x approaches 0 of 1 over x times ln of 1 minus 2x. And multiplying by 1 over x is the same as dividing by x, so I could just rewrite this so that it looks like a quotient. So natural log y is equal to the limit as x approaches 0 of, in my numerator, I will have natural log of 1 minus 2x, and in my denominator, I will have x. And so now, if I were to check, now that I have a quotient, if I were to check my limit, if I plug 0 in, 2 times 0 is 0, 1 minus 0 is 1, and in the numerator, natural log of 1 is 0. In my denominator, if x is 0, my denominator goes to 0 as well. Okay, so now L'Hopital's rule. Okay, so when I do L'Hopital's rule, I get the natural log of y is equal to the limit as x approaches 0, and now I have to take the derivative of my numerator. Again, derivative of natural log, 1 over the stuff times the derivative of the stuff. So I'm going to have 1 over 1 minus 2x times the derivative of 1 minus 2x, which is negative 2. And then in the bottom, the derivative of x is 1. So if I simplify this, the natural log of y is equal to the limit as x approaches 0 of negative 2 over 1 minus 2x, which is all divided by 1. So I can just write it exactly like that. And now I can plug in 0 because I no longer have an indeterminate form. Now I have negative 2 as my numerator. So when I plug in 0, I get natural log y is equal to negative 2 over 1 minus 2 times 0, which means natural log y is equal to negative 2 over 1, which is negative 2. So if natural log of y is equal to negative 2, then e to the ln y is equal to e to the negative 2, and y, which is the answer to our limit, is equal to e to the negative 2 power, or 1 over e squared. So the answer to our limit is 1 over e squared. That one was a little bit easier than the last one.